Okay, fine. The recording is beginning. Okay. Thank you for letting me record. Okay, let's open the school book. Okay. So I'm happy to see that you are 5 people today. This is a nice, a nice, a nice gathering. I like it, and I thank you for that. But this is also for you, not for me, because I don't need these things any longer. Fine. So this is in Romanian, I'm afraid, because these are lectures from a few years ago. Okay. So I hope you won't mind because we'll talk English over this. Okay. I prepared more lectures because I found some very nice examples over the internet, and I said I should present them to you. So we are talking about a really nonlinear control technique specific to nonlinear systems called feedback linearization. Feedback linearization. For instance, look at this one, okay? These are some lectures from 2010 from the KTH. That's the Royal National famous Swedish University. Very, very high in the rankings in the world. And then I've got this lecture from this guy, okay? Feedback control, feedback linearization. I don't know who this guy is, and I don't know this university either. But apparently this is a lecture from mechanical engineering, if you look. This is not wrong because essentially nonlinear systems stem from mechanical engineering, okay? That's why we always talk about the pendulum. That's or the van der Pol oscillator, okay? Because these are nonlinear, peculiar nonlinear things. No, if I'm not mistaken, and I don't think I am, nonlinear stuff has been built on mechanical examples rather than electrical stuff. Okay. Then we've got another nice material from some other guys. Okay. And then we've got these lectures. Okay, this is from some university in the Arab countries. Okay, I should look up this university. Okay, so we've got a lot of material we can discuss on. Okay, because this is an interesting subject, and it has some linear. If you people remember linear dynamical systems from the second year control systems course in the second year, from the TSA course as we know it. Okay, we are going to recall some notions from those days, controllability, observability, in terms of nonlinear systems, which are different because they are different. Reachability and observability still exist in the nonlinear case. However, they are complicated and quite different from what we know from the linear perspective. However, there is a nonlinear larger counterpart, and the linear case can be considered a particular instance of that approach. Okay, let's first look at the notes in Romanian. They have been written because I showed you here the authors. They have been written by Alex Țiclea, who left, and by Radu Ștefan, or your co-teacher in this lecture. Okay. So it's their notes, but I'm going to present them to you. I took this subject in 2006. That's about 14 years ago, in a PhD course. Because when I had my PhD in the Netherlands, we were compelled to take doctoral courses. You also have to do if you start a PhD. Also in our university, the first semester you have to take courses, and we took advanced graduate courses, and one of them was called exactly nonlinear control. And one of the subjects, and I didn't find the notes because I was trying to bring you, but I'll bring them to you during the vacation. I'm going to scan them and upload them over the internet in Moodle. All this material is also on Moodle. Just keep in mind there are folders with books and other stuff, and you can find all this material on Moodle as well. So we are talking about nonlinear systems of this form. Okay, nonlinear systems of this form. Okay, and I was telling you I took this subject many years ago, 14 years ago. Okay. Okay. We are talking about these things. What is the question? So you know the classic control scheme. This is your system. Linear, nonlinear doesn't matter. This is U, this is Y. Okay. So now we are changing the paradigm. We are not talking about autonomous systems any longer, but we are talking about control systems. That means a U appears here. Okay. Generally this can be written as this. But this is a particular instance where we call these systems affine in the input. That means that the input appears in a linear form in this way. Why affine? Because you also have X and U. Okay. And this is a very wide class of systems. This is a very wide class of systems. Okay. So this is affine in the input. Okay. And now the question is, how do you build this U? You can build this U, you remember from the TSA course. You can build this U as a state feedback, okay? That's alpha X. Or you can build as an output feedback loop, okay? So we are going to see two particular instances. Oh, sorry, again, I have to make a block here. This is not enough. This is not just a simple, but you have this, okay? Okay, because usually it's difficult to access information about the state. You remember from the TSA course that the state, and from the DCR as well, because last semester we have been talking about linear systems quite extensively, if you remember. So this is your system, and the question is, we are trying to find a state feedback. So this is called in English state feedback. Okay. And also the state feedback is not enough because this is also a nonlinear function. Also a coordinate transformation z equal phi x, such that the transfer from U to V is described by a linear system. That means that once you apply all of this stuff, this system, the resulting system, is linear. The resulting system is linear, okay? This is the problem. This is the problem. I wouldn't say here, I would call here problem formulation. Problem formulation. Am I making sense to you?
Yes.
I hope so. So this is our job now. How to build a state feedback of this form. We can also have an input here, of course, an additional input. How do we build such a control law? How to build such a control law, and how to build a state space coordinate transformation, such that this is what is a state space coordinate transformation? That is the question. I told you this before. Okay, so if you have a linear system, linear case, linear coordinate transformation. Let's remember about the linear case first. Linear coordinate transformation, okay? So a linear system is x dot is ax plus bu. This is a particular instance of the f of x. In this case, f of x is the linear function or the linear operator ax, and g of x is a constant matrix B. Okay? And y is cx. Forget about the d. I don't care about the d now. The question is, how do you change the coordinates? A coordinate change is of this form. Z equal, in the new coordinates, Z equal Tx, where T is an invertible matrix. Okay, X is an Rn, so n is the dimension of the system. T is a square matrix, but also T is invertible or non-singular, invertible or non-singular. Okay, and now we apply this coordinate transformation. In this case, what is X? What is X now? What is X now? Is T inverse Z. You agree? True?
Yes.
You apply T inverse to this relation. Fine. Now we just substitute X into the equations. We just substitute X into the equations. And we get T inverse Z dot. I think you agree that T inverse, being a constant, is not affected by the derivation, by the derivative in time. So is T inverse Z dot is A T inverse Z plus B U, and Y is C T inverse Z. Okay? So nothing is stopping us from multiplying to the left with the matrix T. And this is equivalent actually to, so we have T inverse Z dot is Z dot equals TA T inverse Z plus TB U, and Y is still T C T inverse Z. And these are the new matrices. This is the new A, the new B, and the new C in the new coordinates. A tilde, B tilde, C tilde. Okay. This is, you remember, do you remember this from linear systems? Hmm? You remember this from linear systems?
Yes.
You should. Okay, fine. But now you have a nonlinear system. X dot is f of x plus gxu. Let's take this particular instance. And y is hx. And now z, or how do they define? Z is phi of x. Now, phi is a coordinate transformation if and only if phi is called a diffeomorphism. And I'm going to tell you what this is. So phi, so that means there exists phi inverse, okay, phi inverse, such that phi of phi inverse of x, okay, is equals what? Equals x, okay, and also phi inverse of phi of x also equals x, okay. So inverse, okay, and phi inverse are both smooth. That means they are differentiable, and they are continuously differentiable, and their Jacobians or their gradients are also differentiable. Okay. So how do you do this now? Now, that means, so in this case, it means x is phi inverse z. Okay. Now, what is x dot? What is x dot? That's the question. What is x dot? That's phi inverse of z, all of this dot, or d dt phi inverse z of t. True? This is x dot. Now, how do you make the derivation of this? How do you make the derivation of this? This is d phi inverse of z to dz. Do you remember from the Lyapunov function? V of x dot was dv dx times x dot, true? This is what we knew from the Lyapunov theory from last time. Okay, times z dot. Now, the thing is that here something strange happens in the sense that the -1 can be taken out of the function, and you can write d phi dz -1 z dot. We'll see why we can do that, because it's also explained in the slides. And now, okay, someone has requested a deadline extension for the assignment. I don't know who did that. Someone did, but you could tell me live as well. I'm not biting.
I think it was Mirel, and he's not in the call. He's still at work.
Okay, fine. I'll extend it. Okay.
Thank you.
No problem. Okay, I'll fix it after class. I'll do it after class. Fine. So where were we? Okay. So now, if you need to substitute this back here, so this is x dot. We have computed x dot. This is x dot. So now we just have to substitute it back here. We substitute this back here. Okay. Okay. So we get d phi. Sorry, it's capital Phi. D phi dz inverse z dot equals f of phi inverse z, that's x, plus g of phi inverse z, okay, times u. Okay. So the only thing left now is you can, because this is invertible and we had although it's a diffeomorphism, you can do this. You can multiply to the left with d phi dz. This is matrix. This is a Jacobian, okay? So if phi is defined on Rn to Rn, okay, then d phi dx, okay, is a square. The Jacobian is a square matrix, okay? The Jacobian is a square matrix. So that's why we can do all this. This is a matrix. So then you get z dot in the new coordinates is d phi dz f of phi inverse of z plus d phi dz g of phi inverse of z u. So you see the b now is a bit different from the linear case. It's different from the linear case, okay? And y is h of phi inverse of z. So this is how you apply a coordinate transformation on a nonlinear input-affine system. Does it make sense? Is it a bit clear? These are simple computations. Huh? Well, I hope so. Right. So, a first example. This is an example people always use. It's the pendulum. Do you recognize the pendulum? And now it's a forced pendulum. Now this is a forced pendulum. Okay. So now the pendulum is forced with usually with a couple TC. which we call U. Okay, this is a forced pendulum. This is a forced pendulum, and the force is here. That means that the pendulum is something like I L theta double dot plus B L theta dot plus M G L sine theta, okay, plus U equals 0. This is the equation of the pendulum that easily leads to this system. That easily leads to this system, okay? X1 is the angle theta, and X2 is X1 dot is theta dot, is the angular velocity, okay? And these are the coefficients, okay? They didn't put here, they incorporated IL, so they incorporate IL, BL, MG, and whatever. They are incorporated in A, B, and C, okay? Okay. So the question is, how do you get rid? How do you get rid? Get rid. How do you get rid of the nonlinear term? How do you eliminate the nonlinear term? How? How? So CU, essentially, you need to solve the equation C. Oh, sorry. You need to solve the equation. Okay, solve in the variable U. Okay, the equation, which equation? Minus A sine x1 equals what? What? Cu plus V. Okay. So what is U? Is minus A over C sine x1. Okay. Right? Minus 1 over C V. True? So this is a control law that linearizes with a feedback the system. The resulting system is a linear controllable system, by the way. When we'll talk about these things, like this one. So, what is the drawing for this? What is the drawing for this? Can you follow me, because I need to scroll up and down and left and right on this
Yes.
page. Okay. I hope you. Anyway, I just need to remind you. You can always download and always consult the notebook. The notebook has all the notes from the beginning for all chapters. Okay. This notebook stays there forever. Okay, until the course ends. But you can also download it on your computer forever, locally. Is it clear?
Yes. Yes, we saw it.
So you can always look at this notebook. All these scribblings and notes of mine are left with you. This is my gift to you. Haha. Okay, fine. So where were we? So essentially the idea is this. This is the pendulum. Nonlinear. Okay. So he gets U, and then here you have the output Y, whatever the output is. But then you take this, you build the law U equals, so you build U equals minus A over C sine x1 plus v. Forget about minus 1 over c. That's merely a constant. You make this. You plug this in here. Sorry about this. You plug this in here. Okay? You plug it in, and then the resulting system, okay, this should be V. The resulting system, I should add V somehow. So no, this is wrong. Plus V shouldn't be here. It's this. And then here, you just make, this is the input U, this is this, and this is V. This is V. And then you have plus, plus, okay? Now it's correct, okay? And this, the resulting one, this is a linear system. This is a linear system. Is it clear what we want to solve? The problem, is the problem clear? Huh?
I think so, yes.
Yeah, okay. So this is what feedback linearization does. The resulting system is a controllable linear system with the input V. Of course, you can now easily construct another state feedback for V, because you want to stabilize this. You don't know if this is stable. Fortunately, it's stable because of minus B, if B is positive. But you don't know that. So to be on the safe side, you stabilize the system with the state feedback, like you know from the control system scores of the second year, or from DCR last year. Okay? So that means if you substitute this V finally, then your final control law that does feedback linearization and stabilization is this one. Okay? Is this one. Okay? Now, the problem is that this is easy for such a system. What if the system is some weird stuff, some polynomial weird stuff? How do you build? Do you think it's so easy? What if you have here, for instance, if you remember this example, what if you have here x1 dot is x1 squared plus x2 squared times 1 minus x, and x2 dot is x1 squared plus x2 squared times 1, this is minus x1, this is 1 minus x2, plus u. How do you build u to kill all the nonlinearities? So this is a simple example, because this is a simple controlled example of a mechanical sort. But how do you do this in general? That is the question we need to answer now, because this is a simple case. This is an easy job for the pendulum. Okay? So how do you do this for all nonlinear systems? Okay. So we start talking about sub-problems, smaller problems that build the big problem, that help us solve, whose solutions then, if you add them up, you can build the full solution of the problem. Okay. So we noticed that for eliminating the nonlinearities, a good structure, a suitable structure, okay, to eliminate the nonlinearities, okay, is this one. X dot is ax plus b, a gamma x, this is in x, times u minus alpha x. This is the way how to build it, such that the pair AB is controllable. Do you remember what controllable is? Do you remember what controllable is?
Yeah, we should remember.
You should, then tell me. What you should. this is controllable. So the pair AB, or this system, is controllable if and only if there exists U such that x0 can be taken to x via U. Okay. Okay. So this is x0, or you can start from 0 actually. You can start from 0 actually.
Or if we compute the controllability matrix and it has
Exactly.
a rank.
No, that's what I'm going to tell you about the controllability matrix. But let me just remind you what controllable is. So you start from 0, then there exists U that takes you to x, and backwards, and then backwards. Okay. Now, how do you test controllability? Indeed, you build the controllability matrix. You build a controllability matrix. This is a concatenated. This is an augmented matrix. B, A, B, A square B, and then you stop A to the power n minus 1 B. And the pair AB is controllable if and only if the rank of R is n, is the dimension, yeah, A is n or n, X is Rn, B is Rnm. Okay, so this is controllability. This is controllability, the power to control, the possibility to control the state. Okay, so this is what controllability is. Okay. So what we need for this, the ingredients we need for this setting here, so things work out properly. So we need the pair AB to be controllable. We also need the applications alpha and gamma to be built on, to be defined on some domain that contains the origin, and we also need gamma to be non-zero. Okay. We need gamma to be non-zero for all x non-zero. Okay. Okay. So then the linearization is possible with this U. The linearization is possible with this U. Okay. For which beta? For beta being 1 over gamma. For beta being 1 over gamma. Okay. So now, if here you pick, so you need this to be, equal to V. Okay. So you need to solve this equation in U. Then U is, yeah, indeed, U equals alpha x plus beta xv. So 1 over gamma v. So if you substitute this U in here, then you easily get this controllable linear equation. Okay. Then if you need to stabilize, you just build a state feedback such that this matrix is stable. Hurwitz, or stable, asymptotically stable. Okay. Do you remember what a stable matrix is? A stable matrix is the one with the eigenvalues in C minus. Okay, in C minus. Okay. Okay. So you need to do this, but then you do not have, this is when you have nonlinearities in the input. This is when you have nonlinearities in the input, or this is when your nonlinearities, when f of x can be written as ax plus gamma of x. Okay. But this is not always the case. Okay, it can be if you do a Taylor series expansion, but this is not always desirable, because then you've got an approximation. You haven't got the original system any longer. Okay. Right. Now, how do you, why do you need a coordinate change? Why use a coordinate change and how is it suitable? So it says here a suitable structure through a coordinate change. Yeah, obtaining a suitable structure for a coordinate change through a coordinate change. So for instance, you've got this system. This is a strange system. This is something that I told you earlier. Okay, so this is a general system. This is no longer a mechanical system. I cannot use it like this. I cannot do. Yeah, you cannot do feedback linearization on this. Okay, written like this is useless. How to compute U to get rid of two nonlinearities in two equations? How do you do that? You do that by performing a change of coordinates. So you would like to have, for instance, the first coordinate is Z1. You have this coordinate, and then you have this coordinate. Okay, and you realize that Z1 dot is X1 dot, but X1 dot is this one. X1 dot is this one. You see how nice? So Z1 dot is Z2, and Z2 dot is A sine X2 dot, where the dot is on the whole sign. So this is A cosine. This is A cosine. Oh, Jesus. This is A cosine X2 times X2 dot. So this is A cos X2 times minus X2 X1 squared plus U. Okay. Okay. Exactly that we have it here. So we get this one. Of course, in this case, now the nonlinearity is present only in the second equation. Only the second equation. You can build the feedback linearization with this. With this. Okay. Okay. Because you need U. Okay. So you need this to be linear. You need this to be linear. And how do you make this linear? How do you make this linear? Okay. So U is X1 squared plus 1 over A cos X2 V. Substitute it in here. Oh, Jesus. Substitute it in here. Okay. You substitute it in here. What do you get? What do you get? Z2 dot equals what? A cos X2 times X1 square plus U plus X1 square plus 1 over A cos 1 over A cosine over A cosine X2 V. So this one will simplify this one, and this is 0. Okay? So you get Z2 equal AV, actually. AV. True? Is it true?
Yes, it's true.
Okay. So what happens now? You get input-output linearization. Okay? So that means that linearizing the state equation doesn't necessarily linearize the output equation. Okay? Doesn't necessarily linearize the output equation, because then if, for instance, you pick this output is nonlinear again. Nonlinear. So we didn't do well. We didn't do a good job. We didn't do a good job. But now we are trying to do input-output linearization. So you take this U, and then you get these equations. X2 dot is V because you substitute this. You substitute this. X2 dot is V. Y is X2. Okay. The price is you leave a part of the state to remain nonlinear. So you get, if you do these substitutions, that means somewhere you have hidden, you hide the nonlinear dynamics. Okay, you hide the nonlinear dynamics. You hide the nonlinear dynamics, and then you get hidden dynamics. So in reality, you get this. Now, of course, hide means make unobservable. Okay, do you remember what unobservable is? If x1 is different from x2, you still get y1 equal to 1 y2. This is unobservable. Okay, this is unobservable. And unobservable is that CA is observable. CA is observable. This is about the pair CA because it's about the equation. It's about, you know, observability is about the equations x dot equal AX, Y equals CX. The pair CA is observable if and only if rank of the matrix C, CA to the power n minus 1, we call this matrix Q, the observability matrix, or O, equals n. This is observability. But in reality, you get these unobservable dynamics because you don't see it any longer. Look, x2 equals v, x2 dot equal v, y equal x2. There is nothing. You don't get anything about x1. It's unobservable, you see? So if you want to stabilize, do output stabilization, output feedback, okay, to some constant value, you get this. You get this. But now you get some sort of internal stability issue in this case. You may lose stability if you do this. So this is kind of delicate, you see. Feedback linearization is not straightforward. We have to be careful, but we'll have some notions that help us make this general. Okay, let's have a short break, and then we come back and look at the rest of the material, or we can try to look at some other way of doing these things, feedback linearization. Okay.
Okay.
Let's have a short break. Okay. I'll stop recording now, and I'll do this. I'll start recording again when I get back. Okay.
Right.